There is something happening inside your body right now that most doctors never talk about, most nutritionists have never mentioned, and most health programs have never addressed. And it has nothing to do with cutting carbohydrates, doing more cardio, avoiding inflammatory oils, or taking a handful of vitamins every morning. What I'm about to share with you is something that Dr. Lucas Whitfield, a researcher who has spent decades studying human metabolic function, calls the single most overlooked nutritional gap in modern life. And when you understand it, so many things that have been going wrong in your body are going to start making complete sense. We're talking about a nutrient deficiency that affects an estimated 95% of adults walking around today, and the nutrient in question is classified by the scientific establishment as non-essential. But that classification, as we're going to break down in detail, is deeply misleading and may be one of the most consequential labeling errors in the history of nutritional science. The nutrient is called glycine. It is an amino acid. Specifically, it is the smallest and oldest amino acid known to biochemistry, with origins tracing back approximately 3.8 billion years. The reason it is labeled non-essential is simple. Your body has the ability to synthesize it. In nutritional science, any amino acid the body can manufacture is called non-essential, and that term simply means the body produces it, not that it is unimportant. But here is where the entire framework breaks down, and where millions of people are being left completely in the dark. The question scientists almost never ask is this: how much glycine does the body actually produce, and is that amount enough to meet what the body truly requires on a daily basis? The answer is startling. Your body produces approximately 3 grams of glycine per day through internal synthesis. The average modern diet provides somewhere between 1.5 and 2 grams from food, mostly from small amounts in meat, eggs, and fish. Add those together, and the average person gets around 4.5 to 5 grams of glycine daily. However, emerging data from some of the most respected researchers in amino acid metabolism suggest that the human body actually requires somewhere in the range of 15 grams of glycine every single day to support all of its physiological functions adequately. That means the average person is walking around with a daily glycine deficit of somewhere between 10 and 12 grams every single day. Not occasionally, every day, chronically, over years, over decades. And the body, being extraordinarily intelligent, doesn't collapse in the face of that deficit. Instead, it does something called nutrient triage. Nutrient triage is the process by which the body allocates scarce resources to the most life-critical functions first, and progressively withdraws support from less immediately life-threatening functions as the deficit deepens. Think of it like a blackout in a city. The hospital gets power first, then emergency services, then residences, and the last things to lose power are the streetlights and the decorative fountains. Your body does exactly the same thing with glycine. Dr. Lucas Whitfield has written and spoken extensively about how this triage hierarchy explains a cascade of health problems that modern medicine treats as separate and unrelated conditions, but which actually share the same root cause, a chronic and cumulative deficit of glycine. Let's walk through exactly how this triage works, from the top of the priority list to the bottom, because understanding this sequence will help you recognize what's been happening in your own body, possibly for years. The very first thing your body uses glycine for is the synthesis of heme. Heme is the iron-containing component of hemoglobin, which is the protein inside your red blood cells that carries oxygen to every tissue in your body. Without heme, your red blood cells cannot carry oxygen. Without oxygen, you die. So the body will absolutely and without exception dedicate glycine to heme production before anything else. If you have plenty of glycine, this happens seamlessly and you never think about it. If you are glycine deficient, the body still makes it work. It pulls glycine from lower priority functions and forces them to go without. The second highest priority function in the glycine triage is DNA and RNA synthesis. Your body is constantly replicating cells, producing new skin cells, immune cells, gut lining cells, liver cells, and more. Every time a cell divides, it needs to copy its DNA. Glycine is one of the building blocks required for the nucleotides that make up your DNA and RNA. Without sufficient glycine, cellular replication is compromised. The third function glycine supports is the production of bile salts. Bile salts are produced in the liver from cholesterol and are stored in the gallbladder, and they are absolutely essential for the digestion and absorption of dietary fats. When you eat a meal containing fat, whether it's butter on your vegetables, olive oil in your salad dressing, or fat marbled through a piece of meat, your gallbladder releases bile salts into your small intestine to break that fat down into tiny droplets that can be absorbed through the intestinal wall. Without bile salts, you cannot properly absorb fat-soluble nutrients. Those nutrients include vitamin A, vitamin D, vitamin E, vitamin K1, vitamin K2, and the essential omega-3 fatty acids, EPA and DHA. So you could be taking vitamin D supplements every day, eating fatty fish twice a week, and drizzling olive oil on everything, and still be deficient in all of those nutrients, simply because you lack the bile salts to absorb them. Bile salts also perform another critical function. They help regulate the microbial population in your small intestine. Under normal circumstances, your small intestine should have relatively few bacteria. The majority of your gut bacteria should live in the large intestine. When bile salt production is inadequate, microbial overgrowth can occur in the small intestine, contributing to bloating, gas, poor digestion, nutrient malabsorption, and chronic digestive discomfort. This is the condition known as small intestinal bacterial overgrowth, and it is extraordinarily common in modern adults. Moving further down the triage hierarchy, we get to glutathione. Glutathione is often called the master antioxidant of the body, and for good reason. It is produced inside your liver cells, and it is the primary molecule your liver uses to neutralize and eliminate toxins, heavy metals, environmental chemicals, metabolic waste products, alcohol, pharmaceutical residues, food additives, and pollutants. Every single day, your body is exposed to a staggering number of potentially harmful substances from the air you breathe, the food you eat, the water you drink, and the surfaces you touch. Your liver's ability to handle that toxic load is directly dependent on having adequate glutathione, and your liver's ability to produce glutathione is directly dependent on having adequate glycine. Because glycine is one of the 3 amino acids required to build glutathione, the other 2 being cysteine and glutamic acid. This is why some people seem to tolerate alcohol well, and others feel terrible after just 1 or 2 drinks. Some people can eat processed food occasionally without noticeable consequences, and others react strongly. Some people detoxify well, and others accumulate toxins more readily. Part of that individual variation comes down to how well the liver is supplied with glycine. According to Dr. Lucas Whitfield, individuals who are chronically glycine deficient tend to have depressed glutathione levels and are therefore more vulnerable to oxidative stress, more susceptible to toxin accumulation, and more prone to liver strain over time. Now we come to a place in the triage where the allocation starts to shift, and this is where many people start to notice symptoms in their daily lives. Below glutathione in the priority hierarchy sits GABA, which stands for gamma-aminobutyric acid. GABA is a neurotransmitter, and its job is to act as the primary inhibitory signal in your central nervous system. Think of GABA as the brake system of your brain. It is what allows your nervous system to slow down, settle, and transition from a state of arousal into a state of rest. Without adequate GABA, your nervous system stays in a kind of low-grade, high-alert mode. You may notice this as difficulty falling asleep, racing thoughts at night, a tendency to feel wired even when you are physically tired, difficulty relaxing after stressful events, generalized anxiety, or a sense of being perpetually on edge. Glycine directly supports GABA synthesis, and itself acts as an inhibitory neurotransmitter in the spinal cord and brainstem, helping to slow motor activity and calm the nervous system. The epidemic of sleep disorders, anxiety, and nervous system dysregulation we are seeing in modern adults, and strikingly in modern children, is at least partially explained by widespread glycine deficiency. Children today almost never eat nose to tail. They do not eat cartilage, tendons, skin, organ meats, or bone broth. They eat chicken nuggets, hamburgers, and ground meat products, all of which are almost entirely devoid of collagen and therefore almost entirely devoid of glycine. Hyperactivity, poor impulse control, difficulty with emotional regulation, and anxiety in children could all have a significant glycine component that is never addressed because no one is measuring it. The next function in the hierarchy is immune system support. Your immune system depends on glycine in multiple important ways, but one of the most fascinating involves a specific type of immune cell called a macrophage. Macrophages are the frontline responders of your innate immune system. They patrol your tissues for pathogens, cellular debris, and foreign substances, and they engulf and destroy anything that does not belong. Glycine plays a critical role in regulating the inflammatory activity of macrophages. When macrophages activate and trigger inflammation as part of an immune response, glycine is used to modulate and ultimately suppress that inflammatory signal once the threat has been neutralized. When there is not enough glycine, that off switch does not work properly. The inflammation that was supposed to be temporary becomes chronic. The macrophage system stays in a state of heightened reactivity, and you end up with persistent low-grade systemic inflammation, the kind that underlies heart disease, metabolic dysfunction, autoimmune conditions, accelerated aging, and a host of modern chronic diseases. This is why collagen-rich foods and glycine have historically been associated with recovery from illness, reduction of chronic pain, and improvement in inflammatory conditions. It is not folklore. There is a biochemical mechanism behind it that is completely coherent and well supported by data. Now we begin to move into the parts of the triage hierarchy, where deficiency becomes visible. The skin. Collagen is the structural protein of the dermis, the deep layer of your skin that gives it firmness, elasticity, and thickness. When glycine supplies run low, collagen synthesis is reduced. Collagen production also naturally declines with age, approximately 1% per year after the mid-20s. If you are already running a glycine deficit on top of that age-related decline, the cumulative effect on skin quality is significant. You may notice premature fine lines and wrinkles, loss of skin firmness, a thinning or hollowing quality to the face, and sagging in the areas of the neck, jaw, and body. This is not simply a cosmetic issue. The degradation of skin quality is a visible sign of a deeper structural deficit happening throughout the body's connective tissue system. Below the skin in the triage are fascia, tendons, ligaments, and cartilage. Fascia is the connective tissue webbing that encases and connects your muscles, organs, and structures throughout the body. When fascia loses collagen integrity, you lose body shape, you lose structural support, and you develop chronic tension patterns and pain. Tendons, which connect muscles to bones, are under enormous mechanical stress during any physical activity. Without adequate collagen, they become less resilient, more prone to micro tears, slower to recover from training, and more vulnerable to injury. This explains why so many active, otherwise healthy people experience chronic tendon problems, Achilles tendinopathy, rotator cuff issues, patellar tendon pain, tennis elbow, that seem disproportionate to the amount of stress placed on those tissues. Ligaments, which connect bone to bone and are responsible for joint stability, are similarly dependent on collagen. People who chronically sprain their ankles, have unstable joints, or experience recurring joint injuries often have fundamentally weak ligaments due to collagen deficiency, which traces back to glycine deficiency. Cartilage, the smooth tissue that covers the ends of bones at joints, is almost entirely collagen. Cartilage has almost no blood supply, which means it relies on the fluid mechanics of joint movement to receive nutrients and remove waste. It also means cartilage heals very slowly. When cartilage degenerates, it does not easily regenerate. And cartilage degeneration is the defining feature of osteoarthritis, the most common joint disease in the world. We blame osteoarthritis on wear and tear, but the more accurate framing is that cartilage degenerates when it does not receive the raw materials, collagen and glycine, that it needs to maintain its structural integrity. Bones are next in the hierarchy. Most people think of bone as a calcium and mineral structure, which it partially is, but more than 90% of the protein content of bone is collagen. Bone is a composite material, a mineral phase embedded in a collagen matrix. The collagen provides the flexibility and toughness that keeps bones from shattering under impact, while the minerals provide hardness and compressive strength. When glycine and collagen are insufficient, the collagen scaffolding of bone degrades. Bones lose both their mineral density and their structural resilience. This is a major contributor to osteoporosis and fracture risk in aging adults. Arteries, which are the large blood vessels that carry oxygenated blood from the heart to the body, are also predominantly collagen. The walls of your arteries need to be strong enough to withstand the pressure of blood flow with every heartbeat, yet flexible enough to expand and contract as blood surges through them. That combination of strength and flexibility is provided by collagen. When glycine is chronically insufficient and collagen quality in arterial walls degrades, arterial stiffness increases, blood pressure rises, and vulnerability to atherosclerotic plaque formation is enhanced. Cardiovascular disease is largely a disease of connective tissue failure at the arterial wall, and glycine deficiency is a major and deeply underappreciated component of that process. The gut lining also depends heavily on collagen and glycine. The intestinal wall is lined with specialized cells that are connected by tight junctions, protein structures that keep the gut barrier sealed and selective, allowing nutrients through while blocking harmful substances. When the gut lining degrades, a condition commonly referred to as intestinal hyperpermeability or leaky gut, those tight junctions break down. Undigested food particles, bacterial toxins, and inflammatory molecules pass into the bloodstream and trigger systemic immune responses. Bone broth and collagen-rich foods have long been known to support gut healing, and the mechanism is entirely consistent with what we know about glycine's role in maintaining the structural and functional integrity of the gut lining. Hair and nails are at the very bottom of the glycine triage priority list. They are made of proteins, keratin primarily, but their growth and quality are also influenced by the overall amino acid availability in the body. When glycine is scarce, the body does not waste any on hair or nails. You may notice this as slow nail growth, brittle nails, thinning hair, or hair that lacks luster and breaks easily. Now, the important question is, why are we so deficient in glycine when our ancestors clearly were not? The answer is that our ancestors ate the whole animal. They consumed animals nose to tail, meaning they ate not just the tender muscle meat, but also the bones, skin, cartilage, tendons, ligaments, feet, ears, and organ meats. All of those parts of the animal, the parts we now discard or never purchase, are extraordinarily rich in collagen, which means they are extraordinarily rich in glycine. A bowl of properly made bone broth, simmered for many hours from bones and connective tissue, is one of the richest glycine sources available. A piece of skin-on chicken thigh, a slice of slow-cooked pork belly, a serving of gelatinous braised short rib, these deliver substantial collagen. But a boneless, skinless chicken breast, a lean cut of steak, a piece of fish fillet, these deliver almost no collagen at all. Modern diets, built around convenience, tenderness, and muscle meat, are structurally incapable of delivering the glycine that the human body requires. This explains why glycine deficiency is not unique to vegetarians or vegans, though they are certainly at high risk. It is equally common in carnivores who eat only muscle meat without connective tissue, in children who eat processed foods, in athletes who push their connective tissues hard without rebuilding them, and in older adults whose collagen synthesis is already declining with age. So what can you do about this? Dr. Lucas Whitfield recommends addressing the glycine deficit primarily through food, rather than isolated glycine supplements, and the most practical and powerful way to do that is with high-quality collagen protein powder. Collagen powder, particularly hydrolyzed collagen peptides derived from bovine or marine sources, is extraordinarily rich in glycine and is the most direct dietary strategy for closing the glycine gap. Adding a daily serving of collagen powder to your morning coffee, your smoothie, or a glass of water is one of the simplest habits you can implement, and the downstream effects on sleep quality, joint comfort, skin quality, gut function, immune regulation, and overall tissue repair are profound. However, and this is absolutely critical, collagen does not work in isolation. The synthesis of collagen from glycine and other amino acids is a biochemical process that requires a specific cofactor, vitamin C. Without adequate vitamin C, the enzymes that assemble collagen fibers cannot function. The collagen you eat or supplement cannot be properly incorporated into your tissues if you are vitamin C deficient. So when you begin using collagen powder, You must ensure you are also getting sufficient vitamin C, ideally from whole foods like bell peppers, citrus fruits, strawberries, kiwi, broccoli, and leafy greens, or from a supplemental source if needed. Bone broth is another excellent whole food source of glycine and collagen. A well-made bone broth from grass-fed beef bones or pasture-raised chicken feet and carcasses, simmered for 12 to 24 hours, will be rich enough in gelatin to actually set into a solid when refrigerated, and that gel is primarily collagen. Including it regularly in soups, stews, sauces, or as a hot drink can meaningfully contribute to your daily glycine intake. The transformation that people experience when they begin systematically addressing glycine deficiency can be remarkable. Better sleep quality is often the first thing people notice, typically within 1 to 2 weeks, as glycine's inhibitory neurotransmitter activity begins to calm an overactive nervous system. Joint comfort often improves within 4 to 8 weeks as connective tissues begin to receive the building blocks they have been deprived of. Skin quality tends to improve over a period of months, as the deeper layers of the dermis gradually rebuild collagen density. Digestive comfort, immune resilience, and recovery from exercise all tend to improve as the weeks and months progress. This is not a quick fix. The glycine deficit has accumulated over years or decades, and rebuilding the body's collagen infrastructure takes time. But the investment is one of the most valuable you can make for long-term health, because every single structural system in your body, from your bones and joints, to your arteries and gut lining, to your skin and tendons, depends on this one small amino acid that most people have never thought about. Dr. Lucas Whitfield often says that the modern health crisis is not primarily a disease crisis, it is a nutrient crisis. We have built a food system around convenience, palatability, and shelf life. And in doing so, we have quietly stripped out many of the nutrients that the human body evolved to receive from whole animal, whole food eating patterns. Glycine is the most extreme example of this. It is the amino acid that holds us together, literally, and most of us are running a deficit so large that it is quietly degrading our joints, our skin, our sleep, our immunity, our arteries, and our gut lining, year after year, with no single symptom dramatic enough to send us to a doctor and no test on a standard blood panel that would ever catch it. The solution is not complicated. Get more collagen in your diet. Eat nose to tail when you can. Simmer bone broth. Use collagen powder daily with vitamin C. Give your body the glycine it has been silently craving, and watch what happens when your connective tissue infrastructure finally gets what it needs.